Hello, this is Minson Kim from Seoul National University of Science and Technology. I presented a paper under the theme of improvement of data coverage for ingesting real-time streaming tweets. Here is the table of contents. In the first section, I will introduce the motivation of the paper and present the contributions of the paper. Next, the overall architecture and proposed framework will be presented. Next, I will validate the proposed real-time architecture based on scenario and show the result of experiment. Finally, I will end up my speech with the conclusion and suggestion for future work. Improving data coverage while streaming real-time data is an important issue. In this study, we analyze the coverage limitation for collecting real-time streaming tweets. To resolve this limitation, we present a parallel architecture working with Apache Kafka and Apache Spark streaming to maximize the coverage of ingesting real-time data streams. There have been several research efforts for building real-time data processing architecture. However, all of these existing studies do not propose a complete pipeline for the real-time data stream to improve the data coverage, which is our main focus. The figure 1 below shows that the frequency of tweets associated with cyber attacks dramatically varied over time. In this respect, ingesting streaming data without loss is necessary for a complete tweet analysis. In this study, we make the following contributions. First, we investigate the necessity of a queuing framework for complete processing of real-time data streams by showing that there is a limitation to a rate of collected tweets for a target example keywords. Next, we propose a framework working with Apache Kafka to improve the data ingestion coverage of real-time Twitter streaming. In this framework, we can improve data ingestion coverage by assigning streaming data into multiple queues in Apache Kafka instead of sequentially processing them. And finally, we validate the proposed framework based on actual scenario compared to sequential processing and show it through the actual experiment. The overall architecture is as follows. The first step is data collection. In this study, we target the real-time data obtained through the Twitter streaming API by filtering based on predefined keywords. Next step is data ingestion. One of the main benefits of using Apache Kafka with Twitter Stream is fault tolerance. To take advantage of this, the producer receives data from the Twitter stream for each topic and stores it into a queue as a log without processing it. Processing data is the following step. In here, we process the real-time data streams which are received from Kafka consumer and extract target fields of tweets in batch. The further data analysis can be done, which will further highlight the advantages of our model. After the data extraction, using Apache Spark streaming, we directly passes extracted result into data warehouses by using connector. Now, we compare the two different real-time architectures. In a simple Twitter streaming architecture, ingestion speed cannot cover the generating speed of streaming tweets, as tweets are generated endlessly at a rapid pace. In this figure, the streaming tweets are sequentially collected and stored in the database, and consequently, much portion of them will be lost because the ingestion speed cannot cover the generating speed of streaming tweets. On contrary, in the proposed architecture in the paper, the message queue acts as a buffer for the distributed data stream working in parallel, thereby improving the data coverage. To consume the loaded entries in the message queues at a fast speed, we also adopt Apache Spark streaming to process the data produced by Apache Kafka. The following researches can support the validity of our scenario. Rostater showed that a small sample of data does not adequately represent the overall activity on Twitter. as the streaming API does not consistently look up for top hashtags, and tweets extracted using them have low coverage than tweets using Firehose. The accuracy of analysis can be reduced. In addition, Hernandez-Suarez has represented the strong correlation between the content of tweets and actual cyber attack. Simple architecture in this figure ingest the tweets sequentially in the order in which they are received, resulting in a low data coverage. However, in the proposed architecture in figure B, assuming two messaging queues, the received tweets are ingested in parallel, allowing a much more portion of the streaming data to be ingested. Here, the improvement of coverage will increase as the number of partition queues increase. In this study, we actually ingested tweets associated with predefined cyber attack keywords for 12 hours on April 30, 2021, and we used 400 cyber attack related keywords for this experiment. Figure 4 shows the distribution of ingested tweets. Here, we define two models. The first model, Model A, which constructs a simple messaging queue model using 3-node messaging brokers in Apache Kafka. And Model B, which directly connects to streaming APIs without a messaging queue. According to the result, Model A showed 1.98% better data ingestion coverage than Model B. The graph also indicates that there is a fluctuation in the proportion of tweets ingested at the same time. It shows that the effectiveness of a messaging queue to manage streaming data. Therefore, we need to design an effective streaming framework to maximize data ingestion coverage. Additional experiments to improve the data coverage and ingesting speed has been done after submission of the paper. If single broker is used on Kafka, the tweet collection is limited with 183,600 tweets. On the other hand, by using 3 producers with 3 node brokers with 1 replication factor, we can now collect up to 550,000 cyber-related tweets per hour. The direction of further research will be described in the conclusion section. Obviously, we know that many partitions could lead to high throughput because producers and consumers ingest multiple partitions simultaneously to process data in Apache Kafka. However, we need to determine an appropriate number of brokers to optimize the performance of each broker in terms of end-to-end latencies and throughput at the same time. In this study, we noted that dramatic changes in generated tweets in real time affect the data ingestion coverage, and finally affecting the accuracy of event prediction. By validating the effectiveness of adopting a queuing system for streaming data processing, we compare the data coverage between a simple data streaming architecture without a messaging queue and the proposed architecture incorporating messaging queues with improved processing with Apache Spark. According to the experiment based on the actual scenario, proposed model presented increased data coverage by roughly 1.98%. And here is the following contributions. First, we investigate the necessity of a queuing framework. Also, we propose a framework to improve the data ingestion coverage of real-time tweet streams. And finally, we validate the proposed framework based on actual scenario. The future research is proposed as follows. The maximum coverage will be found assuming that throughput will increase linearly with the maximum available producer. And furthermore, a correlation between the number of partitions and the number of threads in the producer and consumers and the throughput will be discovered. We will also demonstrate that continuous model learning with the proposed improved framework leads to improved accuracy of cyber attack prediction performance. The referenced paper in the presentation are as follows. Thank you for listening my presentation so far. And if you have any questions or suggestions, I'm always happy to answer them. Thank you.